Now we will look at some of the examples of steady flow processes. So there are several processes and we can apply the steady flow energy equation to this process, and we can make some assumptions also in many of these processes. So first let us look at the case of a nozzle. See, this nozzle is widely used in an engineering device to increase the kinetic energy of the fluid, to increase the velocity of the fluid. Here you can see that this is a peculiar kind of nozzle. This is called a convergent divergent nozzle because so first it converges and then it diverges. Usually you will find a nozzle to be a converging only, but to achieve a much higher speed than of the to achieve a max speed, then you have a convergent divergent nozzle. So you can see that this nozzle, so this is our control volume. This is an open system, so this is the control volume we are taking. So mass is coming in, the same mass is going out because this is a steady, we assume that this is a steady flow device. So usually all the nozzles in practical cases, these are steady flow devices. Whatever mass is coming in, that much mass is going out. So you are taking section 1 and section 2, and this nozzle is completely insulated. That means there is no heat flow outside. Okay, this is 0. So now let us apply the steady flow energy equation. So this is the steady flow energy equation we have derived. That is q dot plus m dot h1 plus v1 squared by 2g plus g z1 is equal to w dot plus m dot into h2 plus v2 squared by 2g plus g z2. Right. So this is the general steady flow energy equation. So for the case of nozzle, you know that since it is insulated, this Q is 0, and you know W, you are not getting a work from the nozzle. So it is not producing work. This system, open system, is not producing work. So this is also 0. And you can neglect these also, GZ1 and GZ2, because this nozzle, the fluid enters and leaves at the same level. So you can cancel these two. So you can reduce this equation. So that is Q dot is equal to W dot is equal to 0. So you will get the equation like this. Okay. And if you neglect gz1 and gz2, you will get the final equation as h1 plus v1 square by 2g is equal to h2 plus v2 square by 2g. Okay, so from this equation you can easily find the exit velocity v2. If v1 is given and the drop in enthalpy is also given, then you can easily find the velocity at the exit.